Hello friends, today we will discuss minerals explorations, surface, subsurface, methods including use of remote sensing data. In module 1, we will discuss the introduction to the topic. The major motive in exploring the Earth's surface and its interior is scientific curiosity or the desire to understand better the nature of the Earth. Another key motive is the prospect of economic profit. Improved standards of living have increased the demand for water, fuel and other materials, creating economic incentives. Scientific knowledge has often been a byproduct of profit-motivated explorations. In equal measure, however, significant economic benefits have resulted from the quest for scientific knowledge. Mining techniques can be divided into two common excavation types: surface mining and subsurface, that is underground mining. Mineral targets are divided into two general categories of materials: placer deposits, consisting of valuable minerals contained within river gravels, beach sands and other unconsolidated materials, and lode deposits, where valuable minerals are found in veins, in layers or in mineral grains, generally distributed throughout a mass of actual rock. Both types of ore deposit, placer or lode, are mined by both surface and underground methods. In this chapter, we will discuss about the following topics: mineral exploration basics, surface methods of mineral exploration, subsurface methods of mineral exploration, remote sensing techniques in mineral exploration. With conventional approaches and tools, only a very limited portion of the subsurface regions of the Earth can be studied. Investigators can drill into only the uppermost crust, and the high cost of drilling severely limits the number of holes that can be dug. The deepest borehole so far drilled extends only to a depth of about 10 kilometers, that is 6 miles. Because direct explorations is so restricted, investigators are forced to rely extensively on geophysical measurement. In recent years, data returned by Earth satellites have led to several notable discoveries, as for example, drainage patterns in the Thar region, which are relics of a period when this region was not arid. Many surface and subsurface exploratory projects are undertaken with the aim of locating 1. Oil and gas accumulations and coal beds, 2. Concentrations of commercially important metallic minerals, 3. Deposits of non-metallic minerals, 4. Recoverable groundwater, 5. Various rock types at different depths for engineering planning, 6. Geothermal reserves, and 7. Archaeological features. The main methods of mineral exploration and their applicability, which is whether surface or subsurface, are listed hereunder. Methods and their applicability. 1. Geological mapping, which includes regional and large scale, applicable in surface exploration, sometimes in underground mines also. 2. Remote sensing and air photo interpretation, applicable in surface exploration. 3. Geophysical methods applicable in surface exploration, which are further divided into A. Gravity applicable in surface exploration, B. Magnetic applicable in surface and subsurface explorations. C. Electrical and electromagnetic applicable in surface and subsurface explorations. D. Seismic applicable in surface and subsurface explorations. E. Radiometric applicable in surface and subsurface explorations. The fourth method is geochemical applicable in surface and subsurface explorations. 5. Drilling applicable in subsurface exploration. Geological methods. Geological maps provide exploration agencies or companies with regional geological and geophysical information so that target areas that are considered having a better prospect in terms of mineral deposits may be identified. The cost of undertaking geological surveys, many of which will not prove to be prospective, is high. Geological surveys provide exploration and mining companies with pre-competitive geoscientific data that is designed to encourage the company to undertake further exploration. Geological methods rely on the identification of rocks and minerals and an understanding of the environment in which they are formed. These surveys aim to find what rock types occur at or close to the surface and how these rock types are related to each other, that is, their boundaries, ages, and structure based on known environments for mineralization or models for mineralization. Regional geological surveys can be used to define smaller areas in which more detailed studies can be undertaken. A geological survey can be undertaken using a number of methods depending on the size of a region and the amount of information that is required. Geochemical methods. Geochemical methods involve the measurement of the chemistry of the rock, soil, stream sediments, or plants to determine abnormal chemical patterns which may point to areas of mineralization. When a mineral deposit forms, the concentration of the ore, metals, and a number of other elements in the surrounding rocks is usually higher than normal. These patterns are known as primary chemical halos. When a mineral deposit is exposed to surface processes such as weathering and erosion, these elements become further distributed in the soil, groundwater, stream sediments, or plants, and their pattern is called a secondary chemical halo. Secondary halos aid in the search for deposits as they normally cover a greater area, and therefore the chance of a chemical survey selecting a sample from these areas is greater than from a primary halo area. Different elements have different mobility in the environment, which is based on their readiness to dissolve in water, their density, their ability to form compounds with other elements, and the acidity of the environment. Subsequently, the secondary halo may not contain the metal for which a geochemical survey is searching, but other marker elements. Drilling. Drilling is used to obtain very detailed information about rock types, mineral content, rock fabric, and the relationships between rock layers close to the surface and at depth. Drilling is only used in areas that have been selected as targets from geological, geophysical, and or geochemical methods. 4 drilling methods are widely used, each depending on the type of information required and or the rock types being drilled. 1. Air rotatory drilling, air percussion drilling, mud rotatory drilling, diamond core drilling. Surface mining is done by removing surface vegetation, dirt, and if necessary, layers of bedrock in order to reach buried ore deposits. Techniques of surface mining include open pit mining, which consists of recovery of materials from an open pit in the ground, quarrying or gathering building materials from an open pit mine, strip mining, which consists of stripping surface layers off to reveal ore seams underneath, and mountain top removal commonly associated with coal mining, which involves taking the top of a mountain off to reach ore deposits at depth. Most, but not all, placer deposits, because of their shallowly buried nature, are mined by surface methods. Landfill mining finally are sites where landfills are excavated and processed. Ore reserves suitable for surface mining can be classified initially as relatively horizontal stratified reserves with a thin or thick covering of overburden, stratified vein type deposits with an inclination steeper than the natural angle of repose of the material, so that waste cannot be tipped inside the pit. Massive deposits, deep and very large laterally, such that dumping of the waste within the pit is not possible. Of all the variations of surface mining methods available, the three most common methods only will be described here, namely strip mining, terrace mining, and open pit mining. Strip mining. Strip mining is ideally applied where the surface of the ground and the ore body itself are relatively horizontal and not too deep under the surface, and a wide area is available to be mined in a series of strips. Favorable conditions are relatively thin overburden where 0 to 50 meter maximum, otherwise stripping ration and cost of stripping becomes too high. Regular and constant surface topography and coal layers. Not more than 20-degree variation from horizontal on the coal seam topography can vary more, since pre-stripped can be used to level it, but this is expensive to apply. Extensive area of reserves to give adequate life to mine, that is LOM, and to cover all capital loan repayments, typically more than 20 years life at 4 to 15 meter per annum production. Terrace mining, where the overburden is too thick or the floor of the pit, that is the ore inclination, is too steeply dipping to allow waste dumping directly over the pit, as in the case with a drag line and strip mining. It is necessary to use intermediate cyclic or continuous transport, for example trucks or conveyors, to transport the overburden to where it can be tipped back into the previously mined void. It is a multi-benched sideways moving method. The whole mine moves over the ore reserves from one end to the other, but not necessarily in a single bench. The number of benches used is usually a function of the excavation depth and type of machinery used. Typically between 10 to 15 meter bench height and 1 to 32 benches in the terrace. Open pit mining. This is the traditional cone-shaped excavation, although it can be any shape depending on the size and shape of the ore body. That is used when the ore body is typically pipe-shaped, vein type, steeply dipping, stratified, or irregular. It is most often associated with metallic ore bodies, for example copper and iron ore. It can be used for many deposits that suit the geometry, most typically diamond pipes. The excavation is normally by rope or hydraulic shovels with trucks carrying both ore and waste. Drill and blast is most often used, which makes the process cyclic. Waste is dumped outside the mined out area since no room is available within the pit. Waste is placed as close to the edge of the pit as possible to minimize transport costs. Benches are normally excavated from 2 to 15 meter in height in stacks of 3 to 4, in between which is a crest on which the haul road is placed. When the number of benches in the stack increases, the road gradient increases too. From an analysis of overall slope geometry, it is clear that as steep a slope as possible should be mined to reduce the overall stripping ratio. Mineral and especially waste transport costs comprise the greatest amount of an open pit mine's working cost. Subsurface mining consists of digging tunnels and shafts into the earth to reach buried ore deposits. Ore for processing and waste rock for disposal are brought to the surface through the tunnels and shafts. Subsurface mining can be classified by the type of access shafts used, the extraction methods, or the technique used to reach the mineral deposit. Methods for underground mining. The choice of mining methods is influenced by the shape and size of the ore deposit, the value of the contained minerals, the composition stability and strength of the rock mass, and the demands for production output and safe working conditions, which sometimes are in conflict. While mining methods have been evolving since antiquity, this article focuses on those used in semi to fully mechanized mines during the late 20th century. Each mine is unique, but they all share the goals of a safe workplace and a profitable business operation. Flat room and pillar mining. Room and pillar mining is applicable to tabular mineralization with horizontal to moderate dip at an angle not exceeding 20 degrees. The deposits are often of sedimentary origin, and the rock is often in both hanging wall and mineralization incompetent. Room and pillar is one of the principal underground coal mining methods. Room and pillar is an efficient mining method. Safety depends on the height of the open rooms and ground control standards. The main risks are accidents caused by falling rock and moving equipment. Inclined room and pillar mining. Inclined room and pillar applies to tabular mineralization with an angle or dip from 15 degree and 30 degree to the horizontal. This is too steep an angle for rubber tire vehicles to climb and too flat for a gravity assist rock flow. The traditional approach to the inclined ore body relies on manual labor. The miners drill blast holes in the stopes with handheld rock drills. The stope is cleaned with slusher scrapers. The inclined stope is a difficult place to work. The miners have to climb the steep piles of blasted rock, carrying with them their rock drills and the drag slusher, pulley and steel wires. In addition to rock falls and accidents, there are the hazards of noise, dust, inadequate ventilation and heat. Shrinkage stoping. Shrinkage stoping may be termed as a classic mining method, having been perhaps the most popular mining method for most of the past century. It has largely been replaced by mechanized methods, but is still used in many small mines around the world. It is applicable to mineral deposits with regular boundaries and a steep dip hosted in a competent rock mass. Also, the blasted ore must not be affected by storage in the slopes. For example, sulfide ores have a tendency to oxidize and decompose when exposed to air. Cut and fill mining. Cut and fill mining is suitable for a steeply dipping mineral deposit contained in a rock mass with good to moderate stability. It removes the ore in horizontal slices starting from a bottom cut and advances upwards, allowing the stope boundaries to be adjusted to follow irregular mineralization. This permits high-grade sections to be mined selectively, leaving low-grade ore in place. Vertical crater retreat mining. Vertical crater retreat (VCR) mining is applicable to mineralization in steeply dipping strata. However, It uses a different blasting techniques, breaking the rock with heavy concentrated charges placed in holes, that is craters, with very large diameter, about 165 millimeter to about 3 meter away from a free rock surface. Blasting breaks a cone-shaped opening in the rock mass around the hole and allows the blasted material to remain in the stope during the production phase so that the rock fill can assist in supporting the stope walls. Sublevel caving. Sublevel caving is applicable to mineral deposits with steep to moderate dip and large extension at depth. The ore must fracture into manageable block with blasting. The hanging wall with cave following the ore extraction and the ground on the surface above the ore body will subside. It must be barricaded to prevent any individuals from entering the area. Block caving. Block caving is a large-scale method applicable to mineralization on the order of 100 million tons in all directions contained in rock masses. Amenable to caving, that is, with internal stresses which, after removal of the supporting elements in the rock mass, assist the fracturing of the mined block. An annual output ranging from 10 to 30 million tons is the anticipated yield. These requirements limit block caving to a few special mineral deposits. Long wall mining. Long wall mining is applicable to bedded deposits of uniform shape, limited thickness and large horizontal extensions. For example, a coal seam, a potash layer or the reef, the bed of quartz pebbles exploited by gold mines in South Africa. It is one of the main methods for mining coal. It recovers the mineral in slices along a straight line that are repeated to recover materials over a large area. The space closest to the face is kept open, while the hanging wall is allowed to collapse at a safe distance behind the minerals and their equipment. Backfilling. Backfilling of mine stopes prevents rocks from collapsing. It preserves the inherent stability of the rock mass, which promotes safety and allows more complete extraction of the desired ore. Backfilling is traditionally used with cut and fill, but it is also common with sub-level stoping and VCR mining. Remote sensing is the science and art of acquiring information about material objects, area, or phenomenon without coming into physical contact with the objects or area or phenomenon under investigation. Without direct contact, some means of transferring information through space must be utilized. In remote sensing, information transfer is accomplished by use of electromagnetic radiation. Each band of information collected from a remote sensing sensor contains important and unique data. We know that different wavelengths of incident energy are affected differently by each target. They are absorbed, reflected, or transmitted in different proportions. In many applications, using information from different bands ensures that target identification or information extraction becomes fairly accurate. Need of remote sensing. Remote sensing gives the overview required to 1. Construct regional unit maps useful for small-scale analysis, and planning field traverses to sample and verify various units for detailed mapping. And 2. Understand the spatial distribution and surface relationships between the units. In reality, the topography, structure, superficial materials, and vegetation combine to facilitate geological unit interpretation and mapping. Optimal use of remote sensing data, therefore, is one that integrates different sources of image data such as optical and radar at a scale appropriate to the study. Applications in structural mapping. Structures can indicate potential locations of oil and gas reserves by characterizing both the underlying subsurface geometry of rock units and the amount of crustal deformation and stress experienced in a certain locale. The main advantage of remotely sensed data in structural mapping is that they provide some information on the spatial distribution and superficial relief of these structural elements. Radar is well suited to these requirements with its side-looking configuration. Imaging with shallow incidence angles enhances superficial relief and structure. Shadows can be used to help define the structure height and shape, and thus increasing the shadow effect, while shallow incidence angles may benefit structural analysis. Applications in lithological mapping. Mapping geologic units consist primarily of identifying physiographic units and determining the rock lithology or coarse stratigraphy. Mapping geologic units consists primarily of identifying physiographic units and determining the rock lithology or coarse stratigraphy of exposed units. These units or formations are generally described by their age, lithology, and thickness. Remote sensing can be used to describe lithology by the color, weathering and erosion characteristics, whether the rock is resistant or recessive, drainage patterns, and thickness of bedding. Unit mapping is useful in oil and mineral exploration. Since these resources are often associated with a specific lithology, structures below the ground which may be conducive to trapping oil or hosting specific minerals often manifest themselves on the Earth's surface. By delineating these structures and identifying the associated lithology, geologists can identify locations that would most likely contain these resources and target them for exploration. With conventional approaches and tools, only a very limited portions of the subsurface regions of the Earth can be studied. Investigators can drill into only the uppermost crust, and the high cost of drilling severely limits the number of holes that can be dug. Because direct exploration is so restricted, investigators are forced to rely extensively on other surface and subsurface exploratory methods like geological mapping, remote sensing and air photo interpretation, geophysical and geochemical methods. These methods allow exploration of mineral targets located in placer deposits and lode deposits, where valuable minerals are found in veins, in layers, or in mineral grains generally distributed throughout a mass of actual rock. Thank you.